Thank you.
Our next speaker is Norimasa Tanaka-san from Tsukuba University. He's going to be talking about Hikami, a lightweight hypervisor for emulating RISC-V extension semantics with sale-driven auto-generation.
Okay.
Norimasa-san, please.
Yes.
Yeah.
Okay. Thank you very much for introduction. Okay. Okay. Thank you very much for introduction. I'm Norimasa Takana. Came from University of Tsukuba, Japan. Today, I'm going to present you Hikami, a lightweight hypervisor for emulating RISC-V extension semantics with sale-driven auto-generation. First, I'll provide a brief introduction to RISC-V. RISC-V is a modern open-source instruction set architecture. Its royalty-free nature encourages innovation and allows for significant customization. A key aspect of RISC-V is its modularity. ISA is divided into extensions allowing hardware designers to include only necessary features. However, this modularity has led to a significant challenge. As shown in the diagram, the number of officially RISC-V extensions is growing extremely rapidly, with nearly 150 standard extensions currently defined. In contrast, the number of extensions actually available in Silicon lags far behind. According to our empirical survey, only about 40 extensions have confirmed adoption.
There's a red dot there. It's from your purple. Yeah, that's good.
Yeah. Okay. Oh, sorry. Only about 40 extensions have confirmed adoption in commercial community hardware. This creates a severe adoption gap. This hardware gap is our first problem. Extensions range from simple instructions to complex features with nuances and exceptions. It is impractical to build hardware for every combination, leaving developers without target hardware for early software validation. The second problem is ecosystem stagnation, a chicken and egg cycle between the hardware and software development. While emulators like QEMU exist, they abstract low-level interaction, making a hardware-coupled validation difficult. So how can we bridge this adoption gap? How can we enable early software validation without waiting for expensive silicon? To bridge this gap, we need a validation environment on physical hardware maintaining a native speed for existing code. The key requirements are ease of use, high reliability, and near-native performance. Next, I'll review existing approaches for extending the ISA and their limitations. One approach is hardware-assisted validation using FPGAs. The ROCC interface allows extending the processor with accelerators that are tightly coupled via the on-chip bus. This setup receives the instruction as commands and returns results, enabling hardware-level ISA expansion with a low latency. While high performance, it requires costly FPGA synthesis for every configuration, limiting early-stage software development. Another approach is a firmware-level emulation where projects write OpenSpace H using illegal instruction traps in M mode. While portable, executing emulation in M mode, which is a highest level mode, violates the principle of RISC privilege and incurs high overhead due to lack of virtualization support. To address these challenges I mentioned earlier, we need to choose the right priority level for emulation. Existing M-mode firmware has a high overhead and security risks. U-mode emulation is secure but slow. Our research focuses on Type 1 hypervisor in HS mode, leveraging virtualization for a low overhead while keeping emulation logic isolated. Based on this approach, we developed Hikami. Hikami is a lightweight Type 1 hypervisor specifically designed for RISC-V. Our primary design goal was to keep the trusted computing base as small as possible, focusing only on essential functions like memory management and trap handling. This architecture allows the guest OS to run at near-native speed and provide direct access to hardware peripherals, meaning we can use unmodified and vendor drivers. Emulation logic is implemented as a modular hypervisor modules, corresponding one-to-one with RISC-V extensions and are integrated using the RISC-V system. For example, supporting the ZBS extension requires only adding 2 lines to the configuration file. It drastically reducing a setup cost. Supporting extension requires handling 3 core elements: trapping new instructions, intercepting new CSR or control and status register accesses, and injecting new exception causes. For instruction emulation, when the guest executes implemented instructions, it triggers an illegal instruction trap to the hypervisor. The hypervisor then decodes the instruction and executes its semantics in software by updating the guest register's context, and finally returns the control to the guest as the next instruction. For CSR emulation, the hypervisor intercepts access to the new CSR and diverts them to a virtual CSR state in a protected memory area. For exception injection, we simulate the new exceptions by directly modifying the guest system register, forcing the guest to jump to its exception handler. While this architecture is powerful, implementing these modules manually remains a challenge. Developers must exhaustively list all new instructions and manually write complex bit masking logic for decoders and implement a lot of boilerplate code. This manual process is not only labor intensive, but also highly prone to subtle bugs. So how can we automate this process and ensure its correctness? To solve the challenge of manual implementation, we propose an automated framework driven by formal specifications. As I mentioned, manual implementation is labor-intensive and error-prone. Developers have to manually parse the PDF specifications and transcribe bit patterns into code, which is a major source of bugs and inconsistencies. Our solution is to automatically generate instruction decoders and hypervisor module templates directly from a sales specification. This ensures that our emulation logic is always in sync with the formal ISA definition. So what is SAIL? SAIL is a formal language specifically designed for describing the semantics of instruction sets. It is already widely used by the RISC-V community to generate official documentation and test suites. By using SAIL, we leveraged an authoritative and unambiguous source of truth for all RISC-V extensions. This is what SAIL code looks like. It defines the mapping between the instructions and the binary encodings. Our framework parses this definition to extract the necessary information for automatic generation. First, we generate the hypervisor module templates. The hypervisor module are the core of our emulation system, so it is critical to avoid the implementation gap or logic errors. To achieve this, our framework automatically extracts the extension name, all defined instructions, and all new CSRs directly from the sales source. This ensures that no part of the extension are overlooked during the implementations. The framework produces a RISC template with a match expression for every instruction. The developer only needs to fill in the semantics logic for each case by replacing a to-do macro, like this. This drastically reduces the boilerplate code and prevents the human implementer from overlooking any specific instructions. And the second part of our framework is automatic generation of instruction decoders. To handle traps, the hypervisor must convert raw binary sequences from guest memory into structured instruction object. Writing these decoders manually is extremely tedious and error-prone due to the complex bit field mapping in RISC-V. We automated this by analyzing the encodec maps in SAIL. By identifying the construct opcodes and variable operand bits, a framework can automatically derive the logic needed to identify and disassemble any instruction. Our generation workflow follows 5 steps, from extracting instruction to constructing a deterministic decision tree. The final output is a set of optimized RISC match expressions that provide fast and correct encodings. Our framework builds a hierarchical decision tree from field data. This ensures that every possible bit pattern is mapped to either a specific instruction or an error, providing us systematic coverage of the encoding space without manual errors. The emitted RISC code is clean, efficient, and guaranteed to match the cell specification. By automating this, we eliminate a major class of bugs commonly found in manually written emulators. And finally, we generated automated unit tests to verify the decoders. And the framework synthesizes instructions with random operands, encoding them according to the specification, and then check if the generated decoder can correctly pass them back. This provides an additional layer of assurance for our implementation. Now let's look at the evaluation. We evaluated Hikami from 2 perspectives: emulation performance on physical hardware and overall impact on the system, including resource efficiency and real-time responsiveness. Experiments were conducted on the Milk5 Megrez, a real RISC-V platform supporting the hypervisor extension. For fundamental validation, we targeted the ZBS bit manipulation extension, which is not natively supported by the hardware. We verified that the guest program using these instructions could run correctly on the physical board. This successfully demonstrated that Hikami can provide the correct semantics for unimplemented extensions on real silicon. To measure the emulation overhead, we conducted the number of instructions executed by the hypervisor to handle the single B-set instruction trap. Emulation overhead is approximately 300 instructions per trap, About half comes from the modular dispatch mechanism, a trade-off for ease of use. Hikami is lightweight with a core of about 7,000 lines of code. More importantly, our auto-generation framework provides a huge productivity gain. In the database module, nearly 75% of the code was generated automatically. The developer only had to write 28 lines of isolated semantics logic, which is significantly reduced the potential for human error. Finally, we compared Hikami with QEMU. Using CoreMark to measure environment-wide performance, Hikami maintains 99.8% of native performance. In contrast, QEMU's full emulation operates at only 8.5% of native speed. And in realistic workloads, such as OS boot or driver initialization, an implemented instruction typically account for less than 0.1% of total execution. In these scenarios, Hikami is up to 3.4 times faster than QEMU. This makes Hikami a superior validation environment for complex hardware-coupled software stacks. And to conclude, we propose a system combining virtualization and automation to address the RISC-V hardware gap. First, our lightweight type 1 hypervisor enables a near-native execution with a modular support for new extensions. Second, our cell-driven framework automatically generates a decoder and templates, eliminating manual errors and reducing implementation effort. Third, and finally, evaluation of real hardware shows our system maintains a 99.8% native performance, achieves a sub-microsecond latency, and outperforms QEMU in realistic workloads. This lightweight design provides an excellent foundation for testing and retrofitting new extensions. So thank you very much for your attention.
Thank you, Norimasa-san. There's lots of time for questions. So do we have any questions? So while other people are thinking of their questions, just wanted to ask you first, a lighthearted question, which is, what does Hikami actually mean in Japanese? Does it mean something? Huh? Does the word mean something?
It is a distriction name.
Okay. Oh. Yeah. All right. So one of the things I was interested in knowing is, you trap an unsupported instruction, and then you're going to go to the hypervisor. What happens to the instruction decoding pipeline? Do you just sort of do you start the execution of the decoding of the next instruction, or do you pause that? So suppose there's you take something from the extension, you're not going to execute it in native mode, but the next instruction in the pipeline, do you start decoding and start processing it at all if that's in native code? If that's in native mode?
We decode each instruction one by one.
Okay.
Yeah.
So you're not considering the possibility of you're going to interrupt the pipeline and okay. Yeah. Are there any security implications of running things in HS mode versus native mode? Could you comment on that?
I can solve this aspect. So
there could be some security implications, right? If you're emulating something in hypervisor, yeah, versus how it would have run on if it was really supported on a machine. How do you deal with those information security leakages and so on? RISC-V hypervisor extension supports memory isolation. You have memory isolation?
Yes.
Okay, all right. And you prefer the HS mode over the M mode?
Sorry?
Is the HS mode always preferred over the M mode for security reasons?
Yes.
Okay, All right. Any other questions? Sorry, I've been asking the questions. Yeah. Okay, let's give Norimasa-san a big hand.
Thanks so much.
Thank you very much. And remember,